Thank you very much. Thank you, Perla, for sharing, and thanks to the organizers for allowing me to give this presentation. So there won't be any theorem or proof. So if you want to leave now, please do so. I mean, this is like, and so again, it's indeed it's a collection. I mean, there is a leitmotif you'll see, but you know that's what I'm going to tell. So hopefully it's very practical, and but I only have one example at the end. Actually, not even an example at the end. So still theoretical, but you know this is at the end. You'll see. I'll try to apply something, although hopefully I have the time to do it. So before I forget, let me thank the funding agency. But so this Debraj and Sri now are postdoc. Debraj is a CTP, and Sri is Max Planck in Göttingen. Toby is now doing a postdoc in Imperial, and then is about to start a PhD. So it's been very fun years with them. So I can use this one. So what's the outline? So, well, I'm going to tell you about exact dynamics for solving master equation and in various contexts, and mainly in finite domains. I will not talk too much about unbounded domain, but many of the results, you know, you can look and use in unbounded domains. So essentially, we deal with occupation probability in space and time, if you want, or generating function, and the first passage processes. And so I'll distinguish between the reactive interaction, inert interaction. So, and think about inert interaction as movement in disordered space. So you conserve probability, and when you have reaction, you know, something gets absorbed. Okay, so it's pretty much that what that distinction is. I'll show you that you can go with topology which are not necessarily hypercubic lattices, and I'll tell you about this interesting disorder in different phenomena. I'll give you two or three examples. I'll show you. And then Maris gave a seminar last week about, you know, first passage with correlated movement. So I'll just briefly touch. And so, and then just one slide, what we are working on now in multiple interacting individuals, which is the part which is relevant when you have actual data, no? So if you have lots of ants, that's the experiment we are looking at. Okay, so, well, to start with, since, you know, you can obviously think about continuous variable rather than discrete, so maybe we should ask the question of why on earth are we doing this? And, you know, so to answer, it's probably better to say why, you know, the continuous variable has been so successful, no? And so you will see that, you know, in some cases, it's not that convenient. So now just that doesn't need an explanation in this audience. Well, we can solve exactly this in space and time, but also, which you will hear me say, instead of exact green function, I'll say propagator. So just allow me to use that terminology. And the notation that you can see that I want to point out here is that when you see this symbol, which is a subindex, it's a starting location, localized there, so that you will see for probability and for first passage. So if you want to grasp what I'm showing. Now, all this equation with all these boundary conditions, actually, there probably can be generalized even more, but this is a classical situation that can be solved. And then if you do your various limits, these are all known solution. Actually, yeah, this one are only in Laplace and space, but this, you know, you can find in time and space explicitly. And so now this again, to remind you, these are the reactive interaction. There is some absorption there, you know, and this is the one that's the inert interaction. You know, it's an example of that. So now, of course, this is all 1D. If you go to 2D, if you have some symmetries you can exploit, it's the boundary conditions are simple enough, but then if you start to having multiple boundary geometry which are complicated, then it becomes a complicated, I mean, then of course it becomes a numerical problem, but then often it's too complicated even to keep track of this boundary condition, then you do simulations. And of course you don't want to do simulation, if you want to be precise at the end, no? And so the whole purpose is that as you go to higher dimension, I'll show you that you can sort of exploit the technique that I'm going to tell you about. So, now, what are these problems that, you know, I'm going to show you some sort of results on? These are the classical, imagine you have two individuals. In this case, it's one individual. This is a classical first passage or escape problem. So you have a domain, and then there are locations where you can get out, and you want to think about the time it takes for that to happen. What's the probability? At the end, I mean, I said the animal, of course, the random walkers move, randomly in space. Now, if you have the same sort of problem with the target are just simply positioned somewhere else, these are search processes, what you might call search processes. And this is like, you can think about a forager, and then the individual has to reach either of them or maybe in sequence and so on. So these are all the absorption position, okay? So this is the reactive situation. A bit more complicated if you want, it's a transmission encounter problem. There are lots of locations where two individuals now, instead of being just one, they can meet. And the meeting, again, it's an encounter. And again, you study as a first passage. And then it becomes any of these is an absorption point. So that becomes more complicated if you have more. And this is all the case of the reactive interaction. And now, since I told you about movement in disordered space for the inert, then you can think about that, you can have areas where, diffusivity is bigger or lower than the average, than the rest. You have some partially permeable barrier or some reflecting or impenetrable barrier. And then you can have, boundary here that, just do not make it very straight, this line and so on. So these are all the inert heterogeneity. So, well, as I said, so the difference is that you do not conserve the probability in that context because something gets absorbed, and that's when you actually really study first passage, And in this case, instead you preserve. Now, of course, you can put this in here, obviously, and this is what you will see I'll do. But yeah, but it's very modular. So you can, as you are able to solve this problem, and then you can put this, target points there. It's formally nothing changes. It gets more complicated, but yeah. Okay, so these are the sort of problems we'll deal with. So the reactive interaction, it's a boundary condition at one site. You have that site is absorption or partial absorption. So it's you call it one defective site. When you have the inner interaction, what you're changing this is the movement in left and right, for example, no? So you always have to deal with, pair of sites, no? So they're always paired. Okay, you will see they're always paired. Okay, so now let's start very simple. Some of you probably have seen this. So what's the case when what's a master equation you write for such a situation where you have, the probability of this walker that starts, that when it's an n can just stay with one probability 1 minus q and move into n q over 2, no? So that's your Pn. Well, okay, you can write it as a matrix if you want. And then you have, probability of staying at the next time step and the probability of moving out. Actually, I didn't do the arrow correctly, but anyway. So, no, actually it's correct. Sorry, no, it's the right arrow in because they represent the gain of this probability of being at time t plus 1. Okay. So now, just an example. If you put some reflecting boundaries, I'm talking about bounded domain. You can find this trivial solution. So this is, if you want, it's the eigenvalues of the matrix equation, if you want. And so now this is trivial trigonometric function, and then you can see that your q comes in here, and then you can have q1, so you always move. That's a classical case. But over time, this quantity, except for the case q equals 0, that gives you 1 here. They all die, and so the k equals 0 is the one corresponds to 1 over n. So everything is uniform, It's reflecting boundary. Similar, if you have a periodic boundary, there is, just change this essentially. So now this is a very trivial case 1D. Now this solution, this propagator, as I call it, for 1D were known, pretty much. For the different boundary conditions. But the problem was in 2D. So the problem in 2D is that finding those occupation probability was not that simple, apparently. And why? So what's the difference between the continuous variable is that, if you think about the solution of this problem in the diffusion problem with continuous variable is trivial. It's a product of 1D case, no? And this is not the case in 2D or higher dimension for discrete. And so that's why apparently some of these cases were not known. The periodic was always known, but as you change the boundary, then you have to worry about the boundary. And so apparently in higher dimension were not known. And so these are the typical bounded domain that I tackled. And you can have reflecting periodic. And so this is, you just have to take care about what happens at the outer point. And then you can have different combination in higher dimension, or whichever one can be absorption, the one reflecting, and so on and so forth. So all of these, can be found, and there is a hierarchical procedure to get to this, starting from the lower dimension. So that's why you can find it. Okay. So now I'll give you an example just to see how much more complicated it becomes in 2D. So you can have a bias, for example, this, you can put a bias. So imagine that you have n side, this is the reflecting boundaries, and then you have a bias which just, essentially takes you to the corner, no? The left corner, no? So then you can see now, as you put 2D, then you have n and m, still the structure is the same, t plus 1. You still have a probability of staying if your Q is not 1. And now you have your biases, G1, which is, I think G1 this axis, and G2 is that axis. And G1 negative, you're going, G1 positive, you're going down there. I mean, this way and that way, no? So, and then you can jump along N, or you can jump along M, the other axis, no? So again, you can solve this problem, and not too different from before, is that you have some finite series. These are our trigonometric function. They're much more complicated, but they are trigonometric function. Essentially, it's a function of trigonometric function. And now here you see the coupling, no? Because I said do not decouple compared to the continuous variable. And you can see here now, now as you sum over K and R, now here you see that it's not the product of two functions. No? That's why, so you see the cos pi K over M. And so that was the thing that apparently was not known. And but then once you have it, then you can, for example, this is just to show you, you can trivially plot. I think it was starting. So you have a bias. So in this case, the positive is take you down there. So this way or that way. And then it's a tiny bias, and then you can see you can plot it with fraction of a picosecond. Okay. So this is the simple case. Now let's come back. So this is, I haven't talked about first passer. Now we can talk about first passer. We're still thinking about searcher and target. So and if you're interested in first passer statistics, so again, probably in this audience, I don't think this is very well known. So what is this? This is a renewal equation that you use, and you connect the first passage to the occupation probability. And so if you think about, I missed that one, sorry. So then you can imagine all the trajectory that takes you from R0 to R, and which is your, you can represent all the probability. But if you think about to represent this as all the trajectory that go to R at some earlier time, and then since the process is Markov, then once you are at R, then you think about that you have to think what happens up to time t, and you have to reach R at time t. So then you go around and you come back in the difference between t minus t prime. So you go from R to R, no? So that's and then you consider all possible time t prime. So that's a famous renewal equation, which apparently the first one to do it was Schrödinger. Did you know, Sadia, it was Schrödinger, 1915? Okay, I found out just last year. Okay, so this is a discrete version that came out later, but Schrödinger did in 1915. So now, how do you solve this problem? And you see the connection, because it's a non-local in time. But as you do the generating function, or it's a discrete Laplace transform of this equation, then naturally you get a simple relation between the first passage and the ratio of the, sorry, that should be reversed. The PR0 on top, and this is PR below, okay? So it's a ratio of the occupation probability from the starting location to R divided by probability. I mean, you can see as you Laplace transform this, you get the product of this and that. No? Okay, so now from here, some quantity sometimes is particularly useful if you have a finite space, so trajectory do not go off to infinity. Then you can compute your mean time, and you differentiate this, and that's what you get. So these are the sort of game that you play, Okay, so what happens is you have multiple targets, So this becomes a bit more complicated. Now, the way to go about is that you think about the joint probability that you go from R0 to one target and not the other target. And then you write an equation for that, and then you write the equation for the other situation. So still a renewal, a coupled equation. So you have to think about that. What you have here, I go from here to there for the first time. This is R prime. But you are interested in writing the probability to go from R0 to R prime without, so that symbol is, and not joining R ever. So if you put the first pass, of course, the right trajectory goes through R, but you have to subtract them, no? And so the way to subtract them is that then you consider the one that goes from here to there without going to R prime, which is that object, again, at some earlier time. And then, and then you think about, since you have to reach R prime, no? Because you have to subtract the one from here, then you go from here to there, and you subtract them in the remaining time. So you see, it's a very similar structure to the renewal equation. And then you sum over all possible time. So you write the one the other way around, yeah? So when you're thinking, you try to write this one on the left, and then you solve the problem, no? So you get the joint, and then you can find, so just to show you, if you are interested in the first passage to either of those two, so it's a sum of, the first passage, so this part is the first passage from 0 to R. Notice that you see the structure is that is based on not of this G, so this G gets taken out, so you're interested in the full solution, and then it's the first passage from 0 to from R0 to R, and then you subtract the one that goes to R prime, but then of course you come back to R, no? But then this normalization factor, I mean, it's sort of inclusion-exclusion. If you expand this, you see you keep expanding times that you go from R to R prime and from R prime to R, no? So it's sort of an inclusion-exclusion. And yeah, please. Oh, just, I mean, the distinction is just in the location R prime and R. So yeah. Any D, any topology, any D, this is completely different. Correct. So, yeah, so, and you can see, oops, no, sometimes I miss it, yeah. So, and similar here, I mean, this is the other one. So you go to R prime without going to R. So then you have to subtract all the transectors from R0 to R, and then from R you go back to R prime. Huh? Yeah. No, I mean, you can do analytics. I mean, on the meantime, it's easy. Yeah, this one you just have to do an inversion, 1D integral inversion. So yeah, trivial. Now, the complexity, if you want, once you have, the discretization in space, that, that could be, but this one, I mean, it depends on about these guys, no? So, but, inversion, generating function inversion is just 1D integral. Yeah, is that? I mean, I'll give you some example that, what's convenient, no? I'll come back. Okay, so now, if you want M targets, I remember trying to do this, extending to this was too much. No, it was, so that I did in a different way. And, oh, okay, sorry, this is, if you want, you can compute the mean time. And I forgot to say that. Again, so, I mean, it would have been hard to guess this normalization factor, no? So, but then you have minus factor here, so it's very hard. So you need the full probability to get to those answer, but everything is in terms of first passage when there is only one specific target point, no? So, go from 0 to R, 0 to R prime, and then sort of the permutation between the target points. So you get R to R prime, if it's not periodic, it's not the, no? So it could be a reflecting case. So now, before I give you the general M results for M targets, so let's talk about the partial reactivity, because your target is if fully absorption, it's like a boundary condition, like with the, probability being 0. But if it's partial absorption, you can go through many times before you get fully absorbed, no? So now, and imagine that, and this is what, in principle, this represents. You go through this target many times before you get absorbed. And so, I mean, in general, you can think about intuitively that you have an encounter rate, which is the time it takes for you to get from here to there. And then you have a reaction rate. So think about two quantities. And then there is, interestingly, while you use absorption, which is, it tells you that the sum of the rate is the actual answer, no? Yeah, I mean, if you have one target, if you have multiple targets, it's a much more complicated business. And so this is in, you probably have heard this name. Mathesian's rule is that's the basis of Mathesian rules. Or in chemistry, there is inverse addition law. These are the ones that are used. But, this, I mean, you can show it is valid for one target, specifically. But in general, it's only valid in special case, which are the one that you probably have heard. Motion limited. So the slow rate is the one that survives, and so in that case, or the reaction limiter. Okay, so this is just, and of course, if you have multiple targets, then it's much more complicated, no? And so if you have multiple targets, you have to worry about the formalisms to deal with all of them, and and you can develop it, and so then you can talk about the probability to be absorbed at any of the targets, and of course, in it, what you expect to be, I've just seen the case of 2, you have the permutation to go from one of the targets to the other one, all of the permutation, and from the initial condition to all of the target. No? And in fact, this you can write as a ratio of determinant. And what are these monsters there? Well, you can see. So this F are, where are they? Oh, I forgot to write it. So this Fij, so the one not on the diagonal, are all the one that goes from target J to target I, or see Ji, Ij, So these are, and then the initial condition is on the top, which has to be with, this factor here, from 0 to all the targets. And along the diagonals, this is where you have, this is the return probability. That's when it matters, okay? And then if you think about this rho, are all the partial absorption. So it has all the information there. So if rho is 1, then there is no return probability. That term is just 1. Okay, so this is, oh. What, sorry? No, that's the probability. Once you are at that site, there is a probability, you throw a dice, to be absorbed, probability to absorb. Yeah. Now, if you want, you can build, you differentiate these determinants, and you can build the mean reaction time. Turns out to be made out of this expression. And again, so of diagonal elements of the matrix T, because T1 is built from T, T0 is built from T. Or the matrix T is like between the permutation of all these targets. And again, the mean return time comes into play along the diagonal elements. And again, it's 0. That play no role is if rho is 1. So it's, as soon as you get there, it's full absorption. No? And then the matrix T1 is built from T minus 1. Each element is, you subtract 1. And the T0 is T minus all this first passage from the initial condition to all the sets. No? Okay, so now this is to show, coming back to your question, no? So this is an example of, it's a 4D square of size 21, so it's not humongous, but and then if you try to do simulation, 10 to the 6 is not, reach, the actual answer yet, no? As you can see, no? So it's quite, so we tried to push it for 2 more weeks and no changes. So try to get, so that's the advantage, that if you have this analytic answer, you don't have to worry about doing any simulation because you cannot even reach enough accuracy. So, okay, so no, let me skip this one because what time? What is the time? Yeah, so let me skip this one. So now let me tell you about the application of disease transmission. Of course, in that case, there are 2 individuals or multiple individuals. One is infected, many others are susceptible, and you can reach them in many locations. So that's an encounter problem. Plus, if you are close and when you don't necessarily pass infection for sure, so the probability of absorption is not 1, then it's a partial absorption as well. But the expression that you use is the one I showed you before, no? So now it's this T, the same as before. And so what I want to show you is that your pathogen transmission probability, so this is the example I show you. So rho for each site is when 2 individuals are collocated, there is a probability of passing the infection, okay? So in this case, this is the same setup. I forgot the size of the domain, but this is, one is reflecting, one is periodic. And of course, the period and the initial condition are at the border, at the corner, so they are very nearby in that context. That's why, just after 2 steps, this probability starts from 0, goes up, no? Because it's a periodic. But for the reflecting case, you have to wait for them to meet in the middle, essentially, And so that's why. And then when these probabilities start to decay, that's when essentially you have the maximum. So this is when it starts here, no? So for the reflecting. Now notice that here, when you put rho, so this is full absorption as soon as they meet past infection. Here, on the other hand, you start putting rho smaller and smaller, so you have to meet multiple times, And this is what that's when you go, you're approaching the reaction limit regime. So essentially, this becomes completely, okay. Eventually, the decay exponential because it's a finite domain, but this comes completely flat, no? Because it's equally likely, no? Doesn't matter, okay. So now maybe this movie works. So this is just to show you on a much smaller size domain. You can plot here the, so what do we have? So we have, yeah, this one is, let's see, this is a periodic domain. So these are the initial condition. This is the reflecting. So you will see that this, they light up right away because like they are near neighbors, no? But this one doesn't happen. And you'll see that it lights up only here. So all of these, what I'm plotting in color is a splitting probability. So the probability that you pass the infection there and not somewhere else, no? As you sum all of them, that's what we are talking about, no? So, and then you will see that, you know, this goes up here pretty quickly. And this is the one that you sum over all the sites, no? So, does it work? Yeah. So you see, they can meet and pass infection very close to the initial condition. And then eventually here, when this one goes up, they only meet in the middle, no? So this is like, yeah. So just to give you an idea. And then that one more thing to notice is that, you know, the mean is, the mean of this is very far off, no? Of course, as you start having those shapes, you know, so has lost its real meaning, okay? Now, so since we did this, we were curious, okay, suppose you have an individual, one infected, and, you know, that's what we wrote just after COVID. So I said, what's R0 if you have a spatially explicit, you know, context, no? And apparently, so there was no way to find in the literature that they calculated. And so then we said, okay, let's do it for an SIR model. So you have one infected and the other are susceptible, but, you know, there is a probability of, you know, decay. The infected person can actually lose the infection, no? So there is a time scale for that. And so, and now it turns out that you don't even have to do an inversion, because if you want the actual zero is, you know, it's a number. And so you take the generative function. This is the probability that, no, that's not right. That's not the probability. That's the probability of getting the infected person getting out of the system. Eh? So that's not right what I wrote up there. So, and so what's the basic reproduction number? You can show it. Just simply you take that expression with a determinant if you want, and then you evaluate at 1 minus gamma. So gamma is probability that you get out of the system, or the infected individual lose the infection. And then you can plot it. Now this we did for the square of size n. And of course, you know, then you divide by W, which is the number of individuals there, and then we were able to plot it. Okay, just to show that you can use in this context. Now, probably this is not really relevant for a global pandemic, but, you know, I was actually interested when, if you remember, we were waiting outside the supermarket and so I was asking how many go inside, no? And so I said, well, where does it come, the number, no? So that's why this was motivated by, yeah, please ask me. It's a basic reproduction number. So the way epidemiology compute is that you consider one individual each infected. There is a sea of susceptible individual, and then you count only the infection due to the individual passing the infection to any of these, or the individual present, but not the secondary infection. You don't count the one that you go from the first to the second, and the second infect another one. So you don't count that. So. Correct. That's what the function. Yeah, they're always moving. Yeah, so the point is that they're always moving, and now you have to think about one walkers with fixed targets in a bigger space. You know, these targets are the location where you are. So you always think about, I can meet this individual in all over the space. So, and you don't want to have moving targets, no? So you want to have fixed targets. So you think about, suppose you have two individuals in 2D. So you're going 4D space, you have one walker, and there are some location in that space, in that 4D space, which are, well, yeah, whatever the hyperdiagonal there is, which are the location where you can pass infection. So that means that that individual dies out. Once you pass infection, you don't have any more two walkers, no? Because it's the process, yeah? So it's always moving. Something is always moving. Okay, so now since we wanted to have fun also on resetting, so this is the case of, everybody probably knows about resetting now, maybe. So this is a spatial heterogeneous resetting case. So you have two media, no? Medium 2, medium 1. And the resetting only happens on the left. So all of, wherever, it could be infinite space on this side, and then they all reset with probability R, no? And of course, and you can also move with probability, your Q probability 1 minus R, you can also have a bias, no? So we were interested in finding out what's the first passage if you go from here to a target on the left. Huh? So, and then now here, what we find for an emotional limiter, if you increase the resetting, it's very hard to get to that location, no? Because you keep coming back on. And so as you can see, so as you put R 0.2, so the resetting, you increase the resetting, your initial probability this or that, they do change very quickly into this sort of plateau shaped, which we saw in the reaction limited, you know? So this is the other limit, okay? So, okay, so this is just to show you that, I mean, you can apply in many contexts. Okay, so this, I finished with the reactive cases. So let's think about the inert. So how do you deal with the inert interaction? So these are the cases you can think of, yeah? So highly heterogeneous space. But, you know, I mean, these are, for example, you have this, you can move left and up, but you can also suddenly have a connection there. These are impenetrable barriers, and also these are impenetrable zones. And these are areas where you can have, you know, you slow down, for example, or you might speed up, you know. So the diffusion constant is different there, no? For example. So if you want to treat that sort of problem, and now how do you do it? So this is the master equation without heterogeneity. Suppose, for example, it could be the one that you have non-solution, no? So the psi, if you solve this master equation, you solve that in the box, for example. And then what you have to do, you have to modify wherever you see the heterogeneity, the transition probability. And you know, have to think about this. Remember that I told you there are two sides you have to worry about. It could be one here and one far away, but it could be the neighboring one, no? And so your transition probability here gets modified by this parameter lambda. You know, this lambda could be also negative. Yeah? You can increase that, you know. Well, you have some constraint because you don't want to put this one becoming negative. You know, you have some constraint you have to worry about. But then you sort of think about U and V, no? So you take about these two. That's why they are paired. You take out lambda nu U, and then, well, I mean, with that probability, you have to put it back in somewhere, no? Otherwise, you don't consider probability, no? So you change this transition, and you have higher chance of staying here, no? For example. Now, again, if you have some other connection, you have to worry about the overall sum here. But then you can also have other connection. But this, again, it's all pairwise. Yeah. So now, just to give you an example, so I mean, just an image. So if you have this situation, and then suddenly you want to create a long connection. So now these two rates, you know, because you connect them, suddenly, you know, you change, you know, and you create one that goes there, you know, and one that goes there, for example, no? Just, yeah. Or another one, if you want a sticky site, you know, so that suddenly you change that one, it becomes much bigger because there is a higher chance of staying. And now somewhere you have to take out, you know, this is like two paired connection. You have to worry about, if I want to have a higher chance of staying, I reduce the probability of going left, the probability of going right. And so that's why the thickness here is reduced. Okay, so of course it's all mathematically done, but just to give you the pictorial representation. So in other words, what happens is that once you know where your heterogeneity are, then you modify those in that fashion. So you get an A prime and M. And then you have to solve that equation, okay? So this is like much harder, but you know, I just want to give you the answer. And so what happens is that, again, you have a solution which is given by the probability as a generating function in the absence of any defects, yeah? And then you have a ratio of quantities where, again, inside here, what you have first passes between all the sites where you have made modification. Yeah? Now, again, these first passages are always written in such a way you have one minus the other one, no? Because as you know, as you go from, because they are paired, okay? So that's why I don't want to show you, it's a bit much heavier. So now, just to give you an example, since coming back to your question, how practical it is. Now, I mean, the case here is there are 177, because we counted, 177 correction of the original matrix, okay? So that gives you a determinant, that determinant you saw, of size 177. I mean, matrix 170 by 177. You know, if you parallelize, have half a minute. to get this output. Yeah. No, just to answer that, it's now because essentially what the size of the domain is given by the defects, not by the discretization. Okay. So it was given by discretization, then yeah. So okay. So now this is to show you what is what I want to show is that here you have two targets, and you have the starting point is there, and then you can see these are all local biases, not the global bias. So these are all heterogeneity, and then you have different kinds. And then you can ask here, well, and this is the occupation probability. And that's why this, since you have this direct flow into that area, that's why you have this high density, or eventually the whole thing, you know, becomes uniform. But yeah, so now, oops, what did I do? I just pressed the usual button. Okay, wait a second. Oh, probably it's not. Become inert, exactly. Yeah. So now, just to show you, so if you ask the question, what's the first passage to go here and not there, or vice versa? And of course, you would expect that to be much higher, no? And in fact, if you look at this one, so that probability here is the one that you go here and not there, which is 80% of the full probability, and this is only 20%, no? And so these are things that are practically irrelevant. I mean, now, of course, you rely on the fact that you know where the heterogeneity is. Huh? So, okay, so now, should we stop at, you know, applicability? No, so we push, and then I don't know if it's fun to work with hexagon. I don't know, probably some of you have done it. So, and apparently, you know, I mean, people can try different ways, but we found that the best way is you use this hexagonal coordinate system where, you know, of course, you have three indices, but, you know, they are not linearly independent. So these are all axes at 60 degrees one another. And so then you can see, so if you are here, then you have, you know, all these possible transition to the 6 neighbors. Yeah. And then if you can solve this, you can also solve with internal state, I mean, the honeycomb, so the honeycomb lattice. As you can see now, you can go, because now you have this, you know, you consider a big hexagon, and inside there are 6 sides, but then you can see that this is actually a triangular lattice, no? As you can see. Yeah, this is like the coordinate for which you always maintain, these are the 6, you see, this is 60, 60, 60. No, you don't need to be complex. These are just numbers. Yeah, so you can see there are these are the coordinates. Huh? So 2 minus 2, 0. That's that fellow. Yeah, and you can see that. I mean, you see that, you know, they indeed they maintain always that. Yeah, yeah. So so then when we look at we look first at the boundary condition, so the periodic one. And what was interesting is to find out, as you can see pictorially, you know, what does it mean periodic boundary condition? You have, you know, the same object, you know, surrounding all over space, no? So then you have a mirror image of that object. And then, of course, as you can look, so these are 2 periodic boundaries for the same situation. The only thing you can see, this one is shifted to the left, and this one is shifted to the right, no? So we realize there are 2, so you have to define which one you want, no? And I mean, you just want to make sure that you do it properly. So that means that if you have this hexagon with periodic boundary, then you can see this one is the left shift. Look at this little symbol here. You know, these 2 goes here and here, and that one goes there. And then if you think about the right shift, you know, now notice that this one goes there, and these 2, one goes here, and the other, and the star goes there. No, so this is just because of this. Left and right shift. So now, yeah, so this is just to impress you that you can solve this problem also. And so what I want to show you is that, again, you have this sort of, so the denominator is not, I mean, so not the denominator, sorry, I mean, the eigenvalue is not too complicated, but now you can see that now there is a nested summation. Yeah. So this is like very, very different from the one I showed you in 2D before. There is the sum which are not nested. Okay, so now if you use that one to solve the honeycomb problem through internal states, and then essentially you use this, and because that's the same structure as you can see, and then you solve the honeycomb problem. And again, if you want reflecting boundaries, so you take the periodic and you put some of these defects that I show you in the heterogeneous case, and you put it there. I mean, you only have to put this, not all of that, because it's periodic, no? And so then you can see this one relates to that, this one, where are these? And this one relates to that, and then we're missing the one over there, yeah? So okay, so there is, this determinant is given by the size that of this zigzagging that you have here, no? So, but you can solve it, so in fact, you can find. Now, again, if you have left and right sheet, if you look at first passage, now let's put some absorbing point, and then you can find some differences between the left and the right sheet. I mean, not a long time so much, but you can find also some differences. Okay, let me skip on that. Let me skip that. No, this you can also put a bias. You have, when you have a periodic domain, if you put a bias, then you can, if you miss out initially, then you have to, there are all these, oscillation that comes into place, as they come back and so on. But anyway, so these are all Markov process, but I still give you this. Okay, so this one, let me spend a bit of time on this one because it's interesting, and there are still some things that I haven't completely understood. So let's start with a very simple case, 1D. So you have a symmetric permeable barrier. So if it's asymmetric, it doesn't work. I mean, you don't see that phenomenon. And so just think about that. You have a reflecting barrier here. You start here. You want to reach N. I mean, ignore this arrow for a moment. And then you have the reflecting barrier here at U. I mean, between U and U plus 1. Just think about, I always think about a barrier, something in between two sides. So this is a problem, no? And then you are interested in finding out the mean first passage from N0 to N. So where do you think, now I'm going to shake you. Where do you think is going to be reduced the mean first passage? As you push the barrier here, or as you push the barrier towards the reflecting side? Symmetric semi-permeable barrier. So, as you can see, if you are here, then you have lots of trajectories. Symmetric that you modify. So the original transition rate is modified in an equal way, because you can have that you go more likely here when you come here than that way. The original work is without bias. It's symmetric. You add, no, in this case, I think about decrease. You can also increase, but I reduce the probability that between just these two sides to go left to right, right to left. Yeah, that. I mean, it does work also with bias. It's not this phenomena, but so in other words, you can think about if I put the barrier closer to N0, then initially there are lots of trajectory that gets pushed to the right, no? And but you can think about that, those few that go through, then they have lots of space to wander before they come back to N. So the long times tail is going to be affected, no? Because they go through and so on. So, and then you say, okay, let me compute the mean. I mean, you can, in this problem, you can solve everything, but what? Let's compute the mean. So which one is winning? Oh, I should tell you. None. So if the side here is to the right and the barrier is here, the mean first passage is the same as without the barrier. Yeah?
Count the number of times that you visit every stage, it's one for close and for far.
Okay. Remember, this works also with bias. In as much as the permeable barrier is symmetric, it's also if you have a bias, whichever you want to bias. So now I want to show you, and this is also if you have an anti-barrier, but this is the expression. So this is the expression without that barrier, plus this quantity, and the lambda is this modification of your probability here. Now, do you remember I had A minus lambda in those modification when I put the inner heterogeneities, and so and this you can see it's 0, so it's exactly this term that has no meaning, so it's not there. But of course, if this one is put there, of course it does depend, no? Obviously, no? So, and now just to show you, I mean, this is magic a bit when you think about the shape of these curves. So I plot the first pass probability, where I'm moving the distance between n0 and u. So if you go this way, you are far, so you are towards the barrier, the reflecting barrier. And if you go close to 1, you get closer and closer to where the permeable barrier is. Yeah. So in other words, the distance between them when it's yellow, as I was telling you, if you put it close to the initial condition, then there are lots of trajectories that immediately gets pushed to the right, no? And of course, the first passes quickly grows compared to the other case. So you have higher peaks and so on. But then the one that, and you can see, but this one is also the one that, since the one that goes through, then they have lots of space to wander in it. And the tails is the one that takes the longest to decay. And of course, if this happens, a short time, this happens a long time, somewhere in between, there must be some equilibration. And that's why this, you have this sort of shape that occur. And this is the mean for all the cases in changing this, the position of it, okay? And now, if you put if you put your barrier in between the initial condition and n, then of course the mean is changing between the extreme left and the in between. Yeah. Okay. So now let me tell you another. This is one thing we thought that was a very special case. Actually, there are interesting aspects that happens also in higher dimension. So we were looking at the probability of k visit, again with there is disorder, okay, of a site R. So the number of visits of a site R before you're absorbed by an absorbing site. It's partial absorption, it's fine. So, and then you have the disorder. So you can put more than one, but just suppose you have one site, which a specific site of which has a sticky site. So it's a symmetric site. I mean, symmetric heterogeneity once again. And so this is, we just decided to do in hexagons, but so you start here. This is your final absorption point. Then you're counting the number of times k that you're there, and this is the sticky site. Okay, it doesn't matter where it is, So, but and then they, all this curve for the different. So lambda controls how sticky that site is, and they all collapse on the same curves. Okay. And of course, you can compute. This is probably you can compute also the mean, and then it's the same thing. Now here we have changed this is the partial absorption of the final site. So this is another example of that. No, what time is it? Okay, let me skip this one. This is like, okay. Let me just, okay, then let me just come back to the correlated movement. So Dan talked about it. So as you have correlation in whatever dimension you are in, then you have to worry about that you can go forward with some probability which is different than the one going backwards, okay? And the way you treat the problems is that you consider two states. I think that, yeah, there it is. So the easiest is you make it Markov, because it's just one step, no Markov. And so you have two states, and your states represent the way you're going right or you're going left in 1D. So in higher dimension is, you can do it, but you can't really picture in your mind. But and then this is the case. So C just happens that it's the probability that since your last move that you stay, So and yeah, and the way, so once you construct an object like this, then you can easily solve this problem. And once again, suppose we put periodic boundary, just to make it simple. Then notice that here, I don't know if you notice, but this is the same as the case of the diffusive walker in a periodic boundary domain. So, so this is the same structure. What is changing here, instead of having this simple exponential, this simple 1 minus q plus q cos pi k over n to the power t, now you have a much more complicated object, as you can see. This is the correlated case. So, and so now, well, okay, there are discussions also. What's the type of boundary when you think about correlation? Think about that as you hit it, then you come back and you maintain continue your correlation this way, because you can also think about that you keep trying to stay close, hitting again the boundary and so on and so forth. So in that case, as you come back, then a long time in the finite space becomes diffusive. And in fact, I mean, the steady state is that one. But then you can see the classical scenario, or you have the two peaks. You know, if you start with equal probability left and right at the first step, then you can see there is a two peak, then they broaden, and eventually becomes, you know, steady state over there. And okay, let me skip this one. Again, if you do the first passage, you know, then talked about it. So the only thing that probably is worth telling you now that I'm finishing is that if you compute the first passage in this case, then so this, I think the orange was periodic, and this is reflecting. Okay. But anyway, what I want to point out to you is that, so in this case, if you compute the mean, these are the arrow. When you compute the mean, then of course, somehow is related to the function, no, to the peak. But in this case, you know, the actual probability is very small. So I mean, your mean time, which you know, always worry. I mean, gives more weight to the indirect trajectory. But in this case, it becomes completely useless. No. So then in this context, I just wanted to stress it. And now, just to finish, now, okay, this is the one that. So when you start thinking about multiple individuals, you probably know that people talk about the first passage time, because it means you have n individuals. What matters is sometimes which is the first among n individuals they reach, no? And so this is a well-known expression that you look at. You have the survival of the n-1, and then you worry about the first passage of one of them when they're all identical. Huh? So this is, you know, since the 70s or even before was known. Now, when they are non-identical, well, you just generalize this. And now you can see that you have to worry about, so you have k classes. So these n individuals have different classes. And you can have all sorts of behavior, no? So, well, in as much as Markov, let's say. Actually, I shouldn't say Markov, because, you know, you can also have correlated. But, and so here, now you worry about the one which has the class H, which is reaching, you know, the specific site as you're interested. And suppose you're interested in splitting probability, then it all goes here, no? So you have a complete general procedure to get at this. Now, again, these are non-interacting walkers, you know, and this is the one that we are using in studying these ants. Now, just to show you, and then I'm finished. So this is the case. Well, let's see. So what we did, so this is a 1D case where we have one walker or multiple walker. I think it was just 6. And there is so 5 of the walkers see a permeable barrier. So, I mean, there is a permeable barrier that slows them down to get to the target. And one walker doesn't. And then you can see that this is the first passage, and that as, you know, the barrier becomes more and more difficult to go through, then, you know, the probability of all of them, you know, any of them going to the target is very close to the one related to the single walker, no? So instead, if you have, you know, and if you reduce that one, of course, things change. And I think I'm finished. And this is some of the stuff. I mean, the one in red is the one I've tried to tell you something about. Okay. Anyway, thanks. Yeah. The inert. Okay, so maybe. No, it's fine. So I think it's, where was it? Okay, so we were here to start with. Yeah, that's. This one, yeah. So I mean, they are putting here precisely because you have to imagine you are here. Before you put that boundaries, there was some probability they go right and from right to left. So this is at the 2 pair site, and you are modifying that, killing. So there was a minus lambda, if you remember. You put lambda exactly equal to a, so that you completely kill that transition rate. That. But you're thinking about continuous variable, you're thinking about no, discrete, it's like you're just modifying a rate. I mean, that's why if you have a continuous, I mean, there is some importance of making continuous, then of course, what happens to the point there? I mean, so there are all those questions. Correct, yeah. So that's so this is so correct. And so here, I mean, you avoid that because I mean, this is just I mean, of this one, you mean in any certainly, yeah. Yeah. Yeah, I mean, if you worry about, so in the continuous, I mean, yeah. No, determinant, I have no, there are no singularities. No, there is no singularity there. No. I mean, why you say you're sorry? No, please. So, have I convinced you to use discrete formalism? I know I haven't convinced Satya, because he has aversion to it. No, I'm kidding. But yeah, so the only comment I can make is that, it's for practical problems, if you don't have to, I mean, again, study this sort of specific question about long times and so on, then it does work. Yeah. Thank you.